Let's take a look at an application of Bayes' rule. Suppose we're working on a new doping test and that we want to use this doping test in a big cycling competition, for example, the Tour de France. Let's say that we have the information that you see here on the screen. So we have a new doping test, and it is positive in 95% of the cases when the cyclist that's being tested has actually used doping. And so it's not 100% accurate. If the cyclist, however, did not use doping, then the test still gives a positive result in 15% of the cases. So this means that you have a 15% chance that you get a false positive. Now, suppose that we know that 1 in 5 cyclists actually uses doping during the Tour de France. And just to be clear, this is a number that I completely made up. What is now the probability that the cyclists used doping if the result of the test is in fact positive? Now, this is typically an example where you will use Bayes' rule, because what you know is what the probability is that the test is positive if, for example, the cyclist has used doping. And what we want to know is, well, the probability the other way around, the probability that the cyclist used doping if the test is positive. So we will be working with two events here. So let's say event D is the event the cyclist used doping. And we have another event, let's say the event T, and that is the test is positive. Okay, so what is it we're looking for here? Well, we want to know what the probability is that a cyclist used doping given that the test is positive. So this means the probability that the cyclist used doping given that the test is positive. And so we're computing a conditional probability. And, well, we can use Bayes' rule in this case. So I'm not going to explain where Bayes' rules come from, but we are going to apply it. So Bayes' rule tells us that this conditional probability, the probability that D is true given that T is true, is equal to the probability of T given D times the probability of D. So the probability that this cyclist used doping. Well, that's not everything. Bayes' rule, it's actually quite a large formula. In the denominator, we get the probability of T given D times the probability of D plus the probability of T given D complement, so that means the cyclist did not use doping, times the probability of D complement. So this is Bayes' rule. Well, let's take a look at the numbers that we have to plug in into this formula. So first of all, we have the probability of T given D. Let's take a look at the original problem and see what that probability actually is. So this is the probability that the test is positive if the cyclist used doping. Well, if you look at this text at the top of the screen, you see that the test is positive in 95% of the cases when the cyclist that is being tested has used doping. So this probability is apparently 0.95. Then the next value, the probability that a cyclist used doping, so P of D. Well, let's take another look at the original text. Well, you see here that we supposed that 1 in 5 cyclists actually used doping. So probability of 1 in 5 or 20%, let's say 0.2. Okay, let's now go to the denominator. And well, you probably see that the first term in the denominator is actually equal to the numerator. So we can plug in exactly the same values. because here we once again have the probability of T given D times the probability of the event D. So we can use the exact same numbers, it's exactly the same term. Let's take a look at the second term. So here we have the probability of T given D complement. And so like I already said, D complement is the event the cyclist did not use doping. So the probability of T given D complement is actually the probability that the test is positive if the cyclist did not use doping. What is that probability equal to? We go back to the original text, and there we see that if the cyclist did not use doping, then the test still gives a positive result in 50% of the cases. So that means that the probability that the test is positive if a cyclist did not use doping is, 15% or 0.50. And then finally, the probability of D complement. What is this? D complement is the event the cyclist did not use doping. And what is that probability? Well, we already know that 1 in 5 cyclists did use doping. Well, if 1 in 5 cyclists did use doping, then 4 out of 5 cyclists did not. And so we get a probability of 4 out of 5 or 80%. So 0.8. Well, now we're as good as done because we know we have used Bayes' rule, we have plugged in all the relevant values. And if you now compute this large fraction that you see here, you will get a value of 0.613. So this means that if this new test, this new doping test that we're trying out is positive, then the probability that this cyclist actually used doping is a little over 60%.